So here's a pinout diagram on the right of it. We know that the operating voltage is between 2 and 5.5 volts, so it's perfect for our purposes. We can actually go over that 5.5 volts, which is why we use the 4 AA batteries. Works perfectly fine, and so it's really suitable for our purposes. We know it has an 8 megahertz CPU clock that we have configured to use with the internal clock. It has 5 internal timers, and these timers are used for delays. And those delays are combining the second and the third timer, or the fourth and the fifth timer, to make these 32-bit timers so that we can use them for the delay. And again, it's tied in, these timers, with the 8 megahertz internal clock. We have an analog to digital converter, and those reflective line sensors for our robot, and possibly, say, a thermistor, could be used as input devices. So when they come in as light or as temperature, they're analog by nature. They have to be converted to digital, and they're converted into a 12-bit digital number. Pulse width modulation is a fantastic feature. It allows us to output a pulse wave to control the speed of the motors for our robot. In total, we have 22 digital input and output ports. Okay, so we can read to these ports, or read from these ports, and we can write to these ports. And we can do it in a digital way, so we can deal with ones and zeros there. So we're turning off and on. With port A, we have 5 ports in total, okay, and they are RA0 to RA4 and also RA7. Now, I know you see RA5 over there on your right that I've highlighted there, but we can't use it because it's shared with the programming pin and the master clear. And we've determined that we can't use it just because of the way we've configured our PIC. Port B, on the other hand, we have 16 ports from RB0 all the way to RB15. And that really enables us to use a lot of outputs on this port. So sometimes when you're looking at how to structure your programs or your interfaces that you're designing, it's best to keep all the inputs on one port, so say port A, and all the outputs on another. Although you can mix them, it's just easier to separate them that way. So the important SFRs we have to concern ourselves with before we can really use the PIC is the TRIS A or TRIS B, both of those. And really what that TRIS A or TRIS B register does in the SFR, it teaches the port to be an input or an output. So if you recall this from last year, 1 is an input, okay, and 0 is an output. Lat A or Lat B, okay, writes to the port. Okay, and then if we want to read from the port, we use port A or port B. So if I flip over to the data sheet here, and I'm just looking at the port A register map and port B register map, you can see here for TRIS B and for port B and Lat B, we have RB0 all the way to RB15. Okay, and these are the different pieces of code or commands or labels that you would need to use in your code. You'll see them later. Same thing up here with TRIS A, port A, and Lat A. So if I wanted to use, for example, down here, RB6, then as a way to read from my port, then I would have to teach that port to be an input before I use it. And remember, you're assigning 1s for inputs, 0s for outputs in the TRIS register, and then I would be able to use that as an input. But if I wanted to output, then I would send it a 0 to the TRIS register, and then I would be able to use the Lat B to send that out. Okay, up here you can see that, just highlight here, these bits that are not implemented in 28-pin devices. So if you look up here, wherever you see a 3, okay, so RA11 all the way to RA8 are not used, and we also know that RA5 is not used, and RA6 I believe is not used as well. So we have those 5 ports in port A. Okay, the 13-channel analog to digital converter, or the ADC, has these 13 channels from AN0 to AN5 and then AN9 to AN15. And they're shared with the digital pins. And actually these analog pins are active default inputs. And that's an important consideration because if we are using a pin that is both a digital and an analog pin, and has both capabilities, we want it as an input, we have to tell it to be a digital input first. Otherwise, it will think it's analog because it always defaults to analog. So the important registers we need to deal with here are the ANTS A and ANTS B. So this is what we're going to do to activate it as a digital input if we want it as an active digital input, or we just have to actually leave it as is if we want to use it as an analog input. So that's really important. We'll see that in later tutorials. The add1con1, which is the analog to digital control register, controls the overall operation of the analog to digital converter. And what we're doing here is we're sampling voltage levels continuously, and then we're converting them into a digital number. Okay, and then we're storing that digital number in this analog to digital buffer. And that is just a 12-bit binary number, and it stores it in this register called ADC1 buff 0, and we have actually, I think that's 18 different buffer registers. If I go here to my analog to digital register map, you can see these are the buffers. And it's a 12-bit binary number that gets stored in here after it converts it from analog to digital. Okay, and you can see there's your control register here with all its different bits to help you configure the analog to digital converter. We also have the ANTS A and ANTS B registers here as well in the analog select register map, okay, which are really key as well. All right, other shared functions we have are the 3 PWM channels. I've mentioned that vary the speed of the motors, and they are the OC1, OC2, and OC3. And we can also use this for controlling a servo motor.